Okay, this is going to be our lesson on logistic growth. I think your notes say partial fractions, but we've already done that, so we're just going to do the logistic growth part of this. So we've talked about this in pre-calculus, um, and we just need to talk about the calculus way to discuss about logistic growth. So we know that when things grow exponentially, we talk about populations and things growing exponentially, but we know that really most things that grow exponentially do actually then have to taper off and slow down due to resources being limited, and different things. If we talk about rumors being spread, there's a point where more people already know the rumor than didn't know it, and so it slows down and things like that. So that level that it kind of levels off to is what's called the carrying capacity. And the important thing to know here on how we set up an equation is that what happens is the growth rate is proportional to the current value. So current value of population, say it's population, but it's also proportional to the how far the current value is from the carrying capacity. So that's kind of how the equation comes to be, that we're going to use. So an example of when we can talk about this growth is again like a rumor spreading. So say you have 2,000 students, well then the carrying capacity is 2,000 students, because once all the students know the rumor, then we would be done. So the rate at which the rumor spreads is directly proportional to both the students who have heard the rumor and the students who have yet to hear the rumor. Okay, so we have both of those things. So the curve might look something like this, and this is logistic growth. So you have the students who have, at first, when a rumor starts, it's going to start growing quickly because it starts spreading like crazy. But then once half the students all know the rumor, and that's going to be that point in the middle, it's going to start slowing down, and it's still increasing, but it's going to slow down. So that's what happens on that side of that. So that's kind of what that looked like. And then so what we end up with is, because we've said that the rate of the growth or the spread of the rumor, the rate of change, is proportional to the carrying capacity, or the number of people who know it, I should say it that way. The number of people who have heard the rumor, that's this value. And it's also proportional to where L is going to be the carrying capacity, the number of people left who don't know the rumor. Okay, so that's where this comes from. The key to this problems, or working these problems, is to know what the equations look like, because we can solve this differential equation by using partial fractions, and we can go through a big long process to solve it, and it's really a big mess. And so we would rather know that every single time when you solve it, it's going to look like this. So that is what we would want to remember. So if we have this, so when you see this, if something says it's logistic, or they say the rate of change, and then they give you an example and it looks in this format, or they tell you the change is logistic, then you're going to know that this is the rate of change, where again, L is the carrying capacity and K is a constant that has to be determined by the problem. Okay, so it's a constant that'll be in there, or we have to find it. And then we know that the solution to that, so the Y, not the rate of change, is going to be this equation where you have the carrying capacity in the top, you have the carrying capacity as part of the exponent here, and then the K from this equation over here is also in the formula, and then you have a C that you'll have to find, and then you have a T is your variable for time. So we definitely want to memorize it, okay, because it's not that easy to solve. So this it's kind of a gross little saying here, but it actually works. Lice Okay, you see that? Lice minus licked, LKT. Okay, so kind of use that to memorize it. All right, so to help you remember where the letters go. The most important one, super important, is this one. I need to see this format because if I know it's logistic, a lot of things become super easy, okay? Especially if they ask me things like, what's the limit as the number of whatever happened, whatever the variable is, goes to infinity. Well, as it goes to infinity, we know it's going to approach the carrying capacity. So in either format, I can see the carrying capacity, that's the limit. I don't even have to solve anything. I just know, hey, that's what's going to happen as I go to infinity. We also are going to know that the rate of change is increasing most rapidly at half the carrying capacity. So for the rumor example, there were 2,000 people in the school. It will be increasing the fastest when 1,000 people know the rumor. After that, it will start to slow down, still increasing, but the rate of change of increase will slow down. So knowing this information, that L is the carrying capacity and it's the limit at infinity, and then that we are increasing most rapidly at half the carrying capacity, those are probably answer most of your questions they ask you about logistic. So let's use this example. It is a calculator problem. So you're going to want to use your calculator to answer this. So if you don't have your calculator out, you might want to get your calculator out. And I'm going to go ahead and get this calculator open while we read through the problem, because I'm going to show you and remind you some things about how to store something and things like that. So this is a population of Alaska from 1900 to 2000. And so let me get this out of the way for a second. So this is the model that can show the population of Alaska from 1900 to 2000. So over that 100 years, here's the model that we can show to show how the population changed in Alaska over that time. And they tell you, just like any other problem, they've got to tell you P is the population, T is the years after 1900, T equals 0 corresponds to 1900. So then they say, what is the predicted population of Alaska in the year 2020? So that means I want to know P of a certain time. I already have the equation, so I want to know a certain time. I want to know what we get. Well, if 1900 is 0, then 2020 is 120. So I want to know P of 120, which means it's going to be 895,598 over 1 plus 71.57 e to the negative 0.0516 times 120. Now, I could type that into the calculator, and there's nothing wrong with that if you want to do that. But then what I'm going to notice is it's going to ask me, if you look at your question, a bunch of other questions about this population. So I'm going to choose to store that function so that it's easier for me to do everything I can with it. Now, one way to store it is to graph it. So if I wanted to look at the graph of it, I could see this logistic shape coming out, but it doesn't really ask me anything that necessarily says anything about the graph, so I'm just going to store it. So I want you to remember how to do that. So we're going to add a calculator page, and we're going to type in the function, and then we're going to store it, and we're going to just store it as P of T or P of X or F of X, whatever you want to store it as. I'm just going to use P of T because that's what's in the problem, okay? So I'm only going to have to type in this whole entire equation one time, and then I've stored it, and so I can use different things and solve and do whatever I need to do with it much easier than if I just typed in the whole thing every time I needed it. So I'm going to put negative 0.0516 T, or I'm going to use X, because remember, I just always use X. It's a lot easier. So I'm just going to use X, and then I need to store this. So remember, that's control of the var button that says store, and I'm going to call it P of X. You could have used T in there and stored it and so on, but I'm just going to call it P of X. It tells me I'm done. The nice thing is then I can just do P of 120. And remember, the P turns bold because I've stored that. I hit enter and I get my answer. So now anything I need to do with this equation has now been stored. I can graph it that way because I can literally open a graph page and just say P of X. It'll graph it. I can do all of those things with it. So I'm going to write approximately, and it was 78,000. I need to make this always in front. 781,218. So this would be our approximation and people. Now there's probably some decimals after that, but probably you're pretty safe to do to the nearest person. But if there were some decimals after that, you could go ahead and include those, and then just make sure you have your units. And then technically we should probably say the predicted population is about that many people. Okay, so let's go to the next example. The next part of this example: how fast was the population of Alaska changing in 1920? Well, that means what I want to know is P prime of 20. What is the rate of change in 1920? Well, again, I stored it. So since I stored it, this is super easy to do. All I have to do is remember, shift minus to get your derivative thing. And again, this is why I use X, makes my life easier. I want to do the derivative of P of X. If you use T, you'll put T in both places that I put X. Then remember, control of the equal sign to get my vertical bar. And then I want to evaluate it when X equals 20, because that's what I want to do. I want to do the derivative of the question, and I want to know what the answer is when you get 20, when you plug in 20. So this is going to be approximately 1,678.08, and it's really 078, so we probably should go ahead and get that. And so if you don't remember, just highlight that, hit enter, and you'll get more decimals. So it's 078, and this is people per year, because this was the derivative over time. So that's what P prime of 20 is. So this is how fast the population was changing in 1920. Since it's positive, we would say it's increasing at about 1,678 people per year in the year 1920. If we do P prime of 40, again, already got it stored, but here I can actually just copy this, and then all I have to do, whoops, forgot that I had that other part on there though. Clear that. So now copy this, and then all I have to do is go back here and change that to 40 and hit enter, and I get about 4127. Again, to get my third decimal place, 0.794 or 5. Again, people per year. And then you could do the same thing for 1999. So I'm just going to leave that for something for you to practice. So you can go ahead and do that. You could just hit pause on the video and go ahead and do it real quick. So that's how many people, how fast the population is changing over those certain years. Then this question says, when was Alaska growing the fastest and what was the population then? Well, it's going to grow fastest at the inflection point. Well, the inflection point is half the carrying capacity. Well, the carrying capacity is 895,598 people. So it grows fastest at 89,5598 over 2. Okay, half the carrying capacity. That's when it grows fastest. Now, it says when it was growing the fastest, when was it growing the fastest? So it was growing the fastest at this many people. Okay, but then I have to know at what year was that. So I'm going to have to solve for the time. Well, again, the nice thing is that because I stored this, I simply have to solve when does P of X equal 89,598 over 2, or of course you could get that answer, comma X. So I just need to solve that equation, and then that'll tell me when it happens. So let's look at that. So we're going to do solve, which you can just type solve, or you can go through the menu to find it. I usually just type it. So I want to solve P of X equals 89,5598 over 2. And I'm solving that for X, which is actually T for time. Again, X just makes things easier for me. And so I get that X is about 82.765. So that means about 82 years after 1900. So in about the year 1982, the population is growing the fastest. Okay, so that's what I found. And then what was the population then would mean, again, I would just do P of 82 if you're using 82, and then I find the answer, and then it's about 438,961. Okay, so again, storing, huge help. Okay, storing that in there, very, very, very big help. So now let's get to the bottom there. I don't know why my thing is messed up here. Let's go ahead and scroll down and extend the page. So what does that tell us about population in the long run? Well, in the long run, what they're saying is, what is the limit as t would go to infinity of P of t? Well, the answer is 895,598 is that limit, which tells us that the carrying capacity, or you could say the limit of the population, is 895,598 people. So being the number of people that Alaska is able to hold. That's basically what that's saying. That's the most we can do for resources and food and so on. Okay. So the biggest thing that I think that you need to be able to do is really honestly go from one format to the other, or use either of those two formats to give information. So let's look at example 7. So this is a typical question. They'll tell you the growth rate of a population is modeled by this differential equation. So I need to know that that is logistic. So you notice it fits this format, okay? Here is your Y, only it just happens to be P. So as long as there's a 1 in front of this P inside, then we know that the number in front is the carrying capacity, or the number with the Y inside, and then this goes here, and this will be your K if we need that, okay? So what is the carrying capacity? Well, the carrying capacity is 100. I can tell directly right from this example, and of course we want some units, so 100 bears. Second question says, what is the bear population when the population is growing the fastest? Well, as long as I recognize this is logistic, I can just say since it's logistic, or since the growth rate is logistic. Population is growing fastest. At 50 bears, because if you want to give another reason, half the carrying capacity. Okay, so I don't have to solve it and go through a big process. I already know that's when it's going to happen. Okay, what is the rate of change of the population when it's growing the fastest? So they want me to find dp dt when t equals 50, or p, yeah, t equals 50. No, population is 50, sorry. We want to know what is that answer when the population is 50. So it says, what is the rate of change, so derivative, which is already given, of the population when it's growing the fastest. I just determined it's growing the fastest when there's 50 bears. So that's simply going to be the equation with 50 substituted. And then, of course, you can, if that was free response, you could just leave it, or you just pop that in your calculator and get the answer. But no matter what, make sure you put bears per year. You have to have your units. Okay, so that's the rate of change of the population at the fastest part. Okay, so let's look at example 8. Suppose that we have a population that develops according to the logistic differential equation. So they told us it's logistic. It's dp dt equals, well, here's the problem. We look at it, it doesn't look logistic. It's just not in the right format yet. So we're going to put it in the right format so that we're able to tell what we need to be able to notice out of this information. Okay, so we know that inside the parentheses, we need this to be 1p. So we're going to factor out a p, that's fine. We can see that we need to do that, but we need this coefficient in front here. Sorry, we need this coefficient to be a 1. Okay, right now it's 0.002. So that means I have to factor out 0.002. Okay, because then when I multiply this times that, I'm going to get 0.002p squared. Okay, so that's what I'm going to factor out. And I know it's subtraction. So let's think about that again for a minute. I'm wanting this to be a p all by itself. It has to have a 1 in front. If it does, this is the carrying capacity, and this is k. So that's important. So I factored out what I had in front, 0.002, and also one of the p's. Okay, so I factored that out. So now we're good on the second half. Now I have to think, okay, what do I multiply this by to end up with this 0.02p? Well, I'm going to have to move the decimal 2 to the right to get 0.2p, so this is 100. So take a moment, if you didn't follow that, and try to go through and figure that out. The reason this is very, very helpful is I have now figured out that the carrying capacity is 100 because it's L, and that's all I need actually to answer A, B, and C. So let's look at the questions. It says if P of 0 is 5, what's the limit as t goes to infinity of P of t? Well, it doesn't matter what the population is, the limit is always going to go to the carrying capacity. So it doesn't matter where you start. If that's the carrying capacity, that's the answer. So all 3 of these limits are 100. Okay? Now, it says sketch the solution curves and figure out which one has a inflection point. So let's sketch each one of these solution curves and talk about the differences in them. So if we do the one here for A, so I'm going to actually do A here, and then I'll do B next to it, and I'll do C below. So this is A. So for A, P of 0 is 5. That means right here at 5, I have a point. I know that the carrying capacity is 100. So up here, you're going to have 100. Halfway point is 50. So that's somewhere right here is 50. Well, that means there's going to be, that's where at first we're growing fast, and then when we hit 50, we have an inflection point because now it's still growing, but it's growing at a slower rate. So that's what A is going to look like, okay? And it definitely has an inflection point. But let's go ahead and talk about B and C. So here's B. So the difference is I still have a carrying capacity of 100, but this time here's 50, but I'm starting with 60. So I'm already past the fastest growing point. So I'm just going to grow toward the carrying capacity, but I'm not going to have an inflection point. I'm going to grow and grow slower and slower towards that carrying capacity. So that's the graph for B. C is very different because C actually starts above the carrying capacity. And let me draw this one a little different. Let me put the 100 a little bit lower. So here's C. So here's your 100, but we're actually starting up here at 120. Well, again, it has to go toward the carrying capacity. So this graph is going to go down until it gets down to that 100. So there's your three different possibilities for kind of what logistic looks like depending on what your initial conditions are. Well, the only one that has an inflection point is right here. So the only inflection point is on A. The other two will not change and have an inflection point. So when you think about slope fields and things, these are the things, this in question is super important, these three graphs, to help you answer that question. And this says example 8 again, this is example 9, just cross that off. So here we have a flu virus spreading through, and you're given this logistic equation. Okay, so this time it's solved exactly in the format that we want. Now it says if P of 0 is 50, solve for P as a function of T. Well, here's where I do not want to have to solve this by a long algebra method. I already know that the solution looks like, I already know that it's going to be lice, which is L1 plus CE, there's your lice, minus lit. Okay, I already know I'm going to get that. So we just need to figure out what are those values. So I don't know C, L, K, or K. T is the variable. So I don't know either of those things. But remember that when we're looking at this differential equation, that we get information from that because we have it in the right format. Oh, and I left off the 1, or I kind of crossed over it. Okay, so this right here is going to be K because the format is K, P, and then we have this as the carrying capacity, so this is going to be L. So I now do actually have L, which I can fill in both places, and I have K. So the only thing I'm lacking is C. But they gave me an initial condition, so I can use that to find out what C is. So first of all, I'm going to write it by filling in what we just found. So we know that L is 3,000, and then we have your C that we don't know, 1 plus C e to the minus 3,000 times K, which is 0.001 times T. So 3,000 times 0.001 is, of course, going to be 3. So we'll have negative 3t there for the next equation. Now I'm going to fill in what I was given. I was told that if I plug in 0 for t, I get 50 for an answer. So that means 50 is going to equal 3,000 over 1 plus c e to the negative 3 times 0. Again, negative 3,000 times 0.001 is negative 3. And then t is 0 for this example, because p of 0 is 50. So that means that I have to solve that. So I'm actually going to move, right now I'm going to move that up there out of my way, because I'm going to have to keep going with this in order to have room. So let me extend the page. Okay, So now I need to solve this. So let's go ahead and simplify just a little bit. So I have 3,000 over 1 plus C e to the 0, which I should have just not written because that ends up being times 1. So I really get 50 equals 3,000 over 1 plus C. So to solve this, basically, remember, you just sort of switch these spots. So 1 plus C gets multiplied, 50 gets divided. So I'm going to end up with 1 plus C equaling 60. So C is 59. So what that tells me is P of T is going to be 3,000 over 1 plus 59, because I now just found that, e to the negative 3t. So here is my basic equation. There is P as a function of T. I did not have to do, if I did it the other way, I would have had to do partial fractions and integrate all this, and it would have been a huge mess. But I don't have to do that because I already know the format. So I now solved for P. Okay, the B part of the question, which I had on the other page, so we'll just do B right here, says use the solution to find the population at 2 days. So I just do P of 2. So that's going to be 3,000, 1 plus 59, e to the minus 6 people. Calculator question, that's a number. You can leave it alone, or free response, sorry. If it's not free response, then you need to put it in your calculator and get the answer. And then C says, use your solution to find the number of days that have occurred when the flu is spreading the fastest. Well, remember, it's going to spread the fastest at 1,500 people. So when we have 1,500 equals 3,000 over 1 plus 59 e to the minus 3t. So then we need to solve that. So we're going to actually go through and solve this instead of using a calculator because you need to know how to do it. Going to do kind of that same little thing again, sort of switch places. So we have 1 plus 59 e to the minus 3t equals 3,000 over 1,500. So you're going to have 1 plus 59 e to the minus 3t equals 2. And then we just start getting e by itself. So 59 e to the minus 3t equals 1. We divide by 59. So we get e to the minus 3t equals 1 over 59. And then you just change this to its equivalent ln expression. So we get negative 3t equals ln of 1 over 59. So we simply solve t is ln of 1 over 59 all over negative 3. So that's the time. If it's a free response question, done. If it's a calculator question, stick it in the calculator and figure out how many days it is. If it's a multiple choice question, you might have to use some logs to simplify that, or some properties. So you may want to try that and see if you can get some other formats, especially those of you that know you need to work a little bit on your log properties. So that is what we need to know about logistic functions for the BC test. So we're going to just do a bunch of questions that do the kinds of things that they typically ask you about. And so memorizing those formats will make life much, much easier. So that would be my suggestion for you.